Afternoon.
Good afternoon, Doc.
Okay, so from where my colleagues left off. So my name is Godwin. I'm in statistics. Room 006. In case you have any questions, so you can stop by. Okay, I'm also an economist. My PhD is in economics, not statistics. So, those who have great economics or something might share some common interest in econometrics or something like that. So my plan is to do up to 150 or 155. I have another meeting in town, and then we'll continue next week. I'll probably stay 3 minutes, 105. You know, I can wait for a few more people. Can you hear me, Francis?
Yes, please, I can hear you.
Yes, I can hear you.
Bernice and so on. The sheriff, you know, the new sheriff guy in town. The second someone. Okay, we have Alex, Bernice, Bismarck. Okay, yeah. We have 30 people right now. Okay, so you guys are from all over, chemistry, physics, and stuff?
Yes, please.
Yes, please.
Science. Nutrition.
Environmental science.
Okay. Any background in
Nuclear engineering.
or regression?
No.
Okay, interesting. Okay. Okay, so you'll be fine. It's regression analysis is very interesting. The workhorse of what we do in econometrics, actually. We have some Greek economics. Probably not. Okay. I'll start in 2 minutes. Can you see the slides, please?
Yes, please.
Yes, no. Yes.
Excellent. Yeah, so we'll start in a minute and go all the way to 150 or so. I have another meeting. Okay, so if you realize I'm going too fast, please slow me down, Francis. Have you taken regression analysis at all somewhere in your master's?
No.
No, not at all.
Yeah.
Okay.
Yes.
Yeah. Okay, you've done hypothesis testing, inferencing, and stuff. I know you were taught design, but so this is very interesting. You might relate to this one fairly easily. Okay, it's 105, so I'm going to start. Welcome to Regression Analysis Fact 702. Like I said, my name is Godwin. I'm in the stats department, room 006. Feel free to stop by if you have to use this in your research. Okay, so what's a regression analysis? It's pretty much a statistical technique. We used to study relationship, you know, between two variables, or between one variable on one hand and a couple of variables on the other hand. Okay, it's used largely in economics. There's a field in economics called econometrics, and the workhorse there is regression analysis. Okay, it's used in physics, engineering, and so on. Maybe those of you who did mathematics in Ghana, core maths, sometimes they will say a variable, if I can remember, something varies inversely proportional to something where k is a constant of proportionality. So all those k stuff could be covered from regression analysis. Okay, so you know, in those core maths, they will give you some what we call initial values, when something is 1, another is 2, something initial values, we call them, and then you're able to recover the constant of proportionality and so on. Those values are given to you. If they are not, you collect data and you can recover them using regression analysis. So that's how physics guys use them. So if you want to study relationship between one variable and another one, or like I said, one variable and a couple of variables on the other side, you employ regression analysis. Really cool statistical technique, okay? So take, for example, a researcher who wants to study the impact of fertilizer on harvest, on soybean harvest, okay? You can employ regression analysis. I have used it to study relationship between farm size and productivity, the returns to what we call schooling. If I went to school 1 more year than you did, what would be the difference in our salaries? Okay, you can use regression analysis for something like that. Or the government says, look, we are running free SHS. Can you study the impact of free SHS on mathematics performance? I would employ regression analysis. Okay. So we try to explain one variable in terms of another. And a common example I'll be using, as I've stated, is, for example, your wages. Wage, okay, it's pretty hard to write here, but we call this returns to schooling equation. This is your wage per hour, okay, and let's have a parameter beta 0 and beta 1, school, okay, or education, something like this. Okay, so I want to, so over here, this is wages, the wage people make per hour. This is your level of education. If you end at primary 6, this should be 6 for you. If you have a PhD, this will probably, I'm not sure, but secondary school is like 12. JHS 3 is like 9. So that's how this data comes, 1, 2, 3, and so on. And wage is in CDs or dollars. So the guy wants to study the impact of education on wage, for example. So with two people, if you take 2 people, one went to secondary school, one ended in primary 6, what will be difference in their wages? Something like that, you can use regression analysis to study. Okay, so as you try to explain, so how does differences in our, how do differences in our level of education impact differences in our wages? Okay, something like that. So I want to study this, or like I said, the government says, look, check how free SHS impacts students' mathematics score, and then I write down my model. I'll have mathematics here, for mathematics, and then I'll relate it to some alpha 0. We'll go through this later, you'll be fine. And then I'll represent this by free SHS, some free SHS, and then something like that. Okay, so if I want to study this relationship, how free SHS impact mathematics score, or how your level of education impact your wage, or how fertilizer affects the harvest of soybean, I want to employ regression analysis. But I'm saying that we are confronted with 3 issues. Okay. First of all, let me take this first. What is the functional form between Y and X? The harvest and the fertilizer, what's the functional form? Okay, you are all science students, so you've done mathematics, elective maths. When I say quadratic, you know what I mean. So what I wrote, the returns, this is called the returns to schooling. Okay, if you go to school, what is the returns? What's the benefit? The returns to education. Okay, so this is what I wrote early on. Okay, you could have added this squared. Okay, if I add a square, then I've specified a quadratic form of the model. So whenever you want to study the relationship between 2 variables, you worry about a functional form to specify. It could be a cubic polynomial. This could be logarithmic. Okay, I could put ln here. I'm sure you've done FAST. I used to teach FAST 101 when I was a teaching assistant. So we taught logarithm and stuff here. And I could put logarithm and so on. So you worry about the functional form. How is wages, or how do wages relate to education in Ghana or in the population, for example? How are wages related to people's education? Is it a cubic polynomial? Is it an exponential function? Is it linear? You are confronted with such a functional form to deal with. And there's usually no exact relationship between two variables. So how do you take care of other factors that you do not know? Okay. And then this, I will come to this later. We call it the Ketris parables. Okay. So I keep cleaning my returns to schooling equation. So I specify such a model. And then I estimate, I say,
Recording in progress.
I say, well, if I go to school one more year than Francis does, my wage will be 10 cedis more than his. Then somebody say, well, not quite. I think you did not take care of your work experience. You know, you have a higher number of years of work experience than Francis. And I say, oh, okay. So it looks like I'm missing something. That's the idea of Ketris parables. Then I said, okay, you know, you are right. I need to take care of work experience, the differences experience. Then I said, okay, well, look, I've taken care of work experience. So now I would confidently say this represents the returns to education. And these things will become clear later on, okay? But I just want to explain the Ketris parables. It means other things being equal. So how much will my salary differ from that of Francis if I went to school one more year than Francis did, given that we have the same level of experience? That's the meaning of the Ketris parables, okay? So we like to study this impact and so on. What is the impact of free SHS on the guy's core mathematics score, given that he was a day student? So that's Ketris parables. I am taking care of other things, okay? There's a comment here. Okay, that's fine. Go ahead, Francis. So feel free and shoot some text messages in the chat box. Okay, so for example, I want to study core maths and whatever, free SHS or education and wages. A good place to start is to plot the data. You are all maths students, you are quantitatively solid, so we'll be fine. You plot the data. This is showing Coca-Cola delivery and the time. They plotted some data points and fit a line through it. It's a scatter plot. On the x-axis, or what we call the abscissa, you have the delivery volume here. So the guy is able to deliver whatever, 10 crates or 10 tracks. It's going to take him what, maybe 15 minutes, 30 tracks. It's going to take more hours. Okay, so you plot the data, like I said. If they told me to study the impact of education on wages, I'm going to collect data on you guys, your education and your wages, your education or wages. Or where did the guy, your undergraduate university versus your PhD GPA, or high school you went to in Ghana and your GPA at the undergraduate level? We can study those relationships. So I will collect data on your undergraduate institution and your final GPA, and then I plot it. So over here, we plot the delivery time of these guys and the delivery volume. It turns out that we see a positive relationship. Okay, by the way, any line that looks like this has a positive slope. Any line that looks like this has a negative slope. Okay, you should be familiar with these things. Okay, so this looks like a positive relationship. Okay. Looks like the more they are able to deliver, the higher the time they spend, and that makes intuitive sense. So I want to study how delivery volume is related to the time. Maybe you are the production manager, you are ordering your workers around. Okay, Mondays the store gets busy, Tuesday probably not, Wednesday, Thursday you want to figure out how to spread your trucks. Okay, the delivery guys, and so you are interested in how much you're able to deliver and associated time. You're able to reward those who deliver a lot within a short time and so on. Okay, so you plot the data, you see a positive relationship. Okay, well, so I can specify a linear relationship because I see these points appear to be on a straight line, not exactly straight line, but looks like a straight line might be a good fit. So a simple equation that captures this relationship, okay, is something like this. And this is what we call our regression equation. Okay, so basically a regression equation is a straight line which we fit to a data. to enable us make predictions, okay, or to evaluate the impact of one variable, okay, on the other. So equation 1 on your screen is what we call a regression equation. It's called a simple linear regression model. Okay, and we'll go to the details later. It is also called a 2-variable linear regression, or bi, BI for bi, so 2, bivariate. Okay, it is called linear because of something I will say soon. Let me see what comes next. Yeah. Okay, let me see what's next. Probably it's not coming soon. That may come later. So let me say it now. It's called a linear here. The word linear because, okay, so, okay, let me wait. Okay, let me wait. By the way, so this is a simple linear regression model. I'll tell you why it's called simple and why it is linear. So you specify the model like this. Y is the harvest, X is the fertilizer. X could be the years of education, Y could be the wages. Okay, so you specify, you may have done correlation analysis in your previous statistics somewhere. Correlation analysis studies the linear association between two variables or amongst a couple of variables. Okay, here in regression, we pin down a direction. Okay, so here I am assuming X predicts Y. But in correlation, the direction is not usually of interest to us. Okay, if you have any question, just stop me anytime, okay? So in correlation, we don't really care the direction. Either X influences Y or Y influences X. In correlation, it doesn't say. It just says, well, these guys are related, highly related, they are not positively highly related or negatively, or the correlation is very low. That's correlation. In regression, we begin to think about a direction that, oh, okay, looks like X has influence on Y. And therefore, I keep Y on the left-hand side and X on the right-hand side. Okay. So education may influence your wages. You want to keep education here and wages here. Okay, that's it. So I'm trying to lay solid foundation and then I'll begin to gallop. Okay. Now, your simple regression model looks like this. This is called a dependent variable. Like I said, we are saying maybe wages depend on education. So this is called a dependent variable. It's also called the explained. It is being explained. We are explaining differences in wages using differences in education, something like that. Or explaining differences in harvest or yield using differences in fertilizer. If I use more fertilizer than my neighbor, what will be the differences in our harvest? So it's explained variable. It's also the response variable. How is the harvest responding to fertilizer use? Of course, it is also predicted. How does education predict your wages? Okay. More formally, it is also called regressant. You may find me calling this the response variable. Okay. Response variable. But it has the same name. This is called the intercept. Okay. Intercept is like the mean in the population. And for example, if X is 0, then you are left with beta 0. Okay, so we call it the intercept. Okay. Maybe if you have no education at all, your level of education is 0, you still make some minimum wage. So that's kind of like the intercept. Okay. And then so we've talked about this, we've talked about the intercept. There is a slope parameter. This is called a slope parameter because it tells her how X relates to Y. You have done calculus before. So what is dy dx? Partial dy partial dx is going to be beta 1. And therefore, dy dx is slope, right? So it's a slope parameter here. And this is called the independent variable, also called explanatory variable. All right, it is explaining why, so it's explanatory. There's a control variable. It is also called a control variable. It's also called a predictor. It's also called a regressor. So I'll be using regressor a lot for this guy, and this I might be using response or explain variable a lot. Okay. The next thing to explain is our error term or disturbance. This is called error term. also called a disturbance. Unobservables, also called stochastic term. Okay, so this is how education impact wages. There are other things that impact wage. I might know them, I might not know them. All of them, I throw them in here into the U. For example, experience. Experience impact people's wages. So it's right here, it's inside here. What else? Tenure. Tenure, how long you've been with a single employer? How long? It's called tenure. Tenure is also here. It affects people's wages. So any other variable that I have not observed, I don't have data on it. Okay. For example, if you want to know some secret, maybe how many times people meet their partners in a month, you are not going to get data on that. But if such a data is crucial to your study, you don't have it, it is unobserved, you just assume it is inside U. So U is an error term controlling for all other variables you have no access to. Either they exist, but I'm having a feedback. Either they exist and you have no access to them. For example, intelligence, yes, intelligence or ability. How smart somebody is affects his wages. But I don't have a measure of intelligence. Yeah, in economics, we use GPA, transcript, blah, blah, blah. It's still not a good measure of intelligence or ability. So all variables that I have no access to, that either they are unknown to me or they are known, but I have no way of measuring them, I put all of them in the error term. So this is called the error term. It controls for all other things because there's usually no exact relationship between two variables. So you control for all other factors, okay? Random things happening. Maybe somebody's beautiful, it affects her wages. Somebody's handsome, it affects wages. I don't know. Any other variable, I don't know, I throw them in the error term. So that's the purpose of the U. All those I know, I am supposed to put them here and not put them here. For example, your experience. But I'll come to that later, okay? Now, this is a simple regression because there is only one regressor. Because there's only one regressor, education, for example, we call this a simple regression model. Why is it linear? Because it is linear in the parameters. By the way, these are called parameters. This is, okay, yeah, you see slope parameter and the intercept parameter. This is not squared. This is not squared. This is not square root. This is not square root. This is not exponent. This is not. Because they are linear. This is linear power 1, right? Power 1, linear. That is where the linear comes from. So now you know why it is called a simple regression, because there's only one regressor. Why is it called linear? Because it is linear in the parameters. Something like this, square root of beta 0 is no longer a linear regression model, but it is intrinsically linear because the square root of beta 0, I can just call it alpha 0, and then the model now becomes linear. Okay, so that's like an intrinsically linear, but on the face of it, it is not linear anymore because this is square root. Okay, so that's the source of the word linear. All right. Francis, are we good so far? Going pretty smoothly?
Yes, we are good.
Yes, Doc.
Maybe then when we get to the examples, it may bring everybody to.
What's that? What did you say?
I said, I'm hoping that when you get to the example part, maybe to make it more meaningful for them.
I'll do some examples, but you know, in PhD, we don't do plenty examples, you know. We just give you a flavor and then, you know, you go and worry about the rest.
Okay.
But, you know, I'm a nice guy. I'll show examples, you know.
Okay, thank you.
Okay, so the errors I showed you, the U are assumed to be normally, oh no, I'm going ahead of myself. The errors here, we assume that they have a mean of 0 on the average, okay? So these are like random things affecting our model, like I said. Well, you know, random. I know education, I know experience, I know tenure affect wages. All other things I don't know are error, they are random. So I assume they have a mean of 0 on average. Okay. There's a common example we give. This is your height. If I know your height, I may be able to predict your weight. So maybe when God created us in a population, we all have the same height, something like that. But it turns out that maybe in God's plan, when He designed it, everybody was supposed to have the same height or the same weight, something like that. It turns out that some people are taller than others and so on. But we are assuming that, well, if God made us 100, how is this measured here? Is it inches or something? If somebody's supposed to have 170, some probably like 180 centimeters or so. Okay, I know this in feet. I'm probably 5'8". Okay, so maybe everybody's supposed to be 180 centimeters. Maybe that's God's design, but it turns out we are all not like that. This assumption is saying that, well, we assume our errors here. The errors are assumed to have a mean of 0. In other words, we are all supposed to be 180 centimeters. Some may be 190. That's 10 above, but some will be 10 below. Okay, so some will be plus 10, some will be minus 10. They sum to 0, something like that. So the errors are assumed to have a mean of 0. If something is truly random, they exhibit such characteristics. Okay, another time is high, another time is below. That's characteristics of things that are random. And of course, if something is not random, then you can see a systematic pattern. Okay, that everybody's plus 10 plus 10. That means there is a pattern. Okay, but if it's something truly random, it tends to have a mean of 0. Okay, we call it a mean reversion or something else. So the errors are assumed to have a mean of 0 and an unknown variance. All the other things that affect our wages here, the error terms that I do not know, I assume these are random stuffs. They have a mean of 0 and they have variability. Okay, you know mean already, right? And you know variance. You've done this in your elementary mathematics. We can have x and probably have x minus the mean, something like that. Later on, we will square this deviation. Later, we will square and sum these guys and put under a formula, sum of x. Okay, this is sampling variability, how a set of numbers deviate from the mean, something like that. Okay, we square. Okay, so the variability of our error terms, we assume they have a constant variance. Okay, I will throw more light on that when I get to homoscedasticity. Very interesting, you will see. Okay, now something technical here. We usually assume the errors are unrelated. The U term, we usually assume they are not related. So the U for Francis, when I specify the wage equation for Francis, how Francis' education affects his wage, and then I specify for someone else, I think I saw another name here, Benny's, specify that of Benny's, so that there's an error term for Benny's. I assume there are errors, the error for Francis and Benny's are not related, okay? We usually assume the errors are not related. If they are related, it causes a problem, but there's an easy way they could be related, right? If they were taught by the same teacher in secondary school, the teacher effect may impact them. Or if they are from the same parent, then their errors may be related, because you think of a variable like motivation. Motivation may affect people's salary they make, because motivation, because of motivation, somebody can travel outside the country, somebody may not, and so on. So motivation can affect people's salary. I have no measure for motivation, so I throw it in the error term. And if Francis and Benny's are from the same family, their motivation may be the same. In other words, there's a variable here called motivation, another one here called motivation, and they are related. That's one way you can have the errors being related, okay? There are 2 petrol places where I buy petrol in my neighborhood. They make sure their prices are the same, because for the trotro drivers, 1 pesewa means a lot to them. So if the fuel station, they are on the same line, if the one of them is 1 peso lower, everybody goes to that place. So it seems to me that the errors for such, if you are studying those petrol stations, should be related, because one of them looks at the price of the other and sets the other price and so on. Okay, so that's one way, error terms could be related, but the idea of the error will become clearer as we move on. Okay. Okay, I don't know if I should talk about this, but it is convenient to view the regressor as controlled by the data analyst. Okay, so when I'm going to collect data on your wages, on your education, I can meet Francis at Bush Canteen and say, hey, Francis, what is your wage? He says 10,000. What is your level of education? 14. I have a master's or something. So random. Okay. This, I don't know this. I don't know what Francis is going to tell me for this. I don't know what he's going to tell me here. So it's just a random sample. That's one way you collect data. What this means is that here, it is convenient to view the regress as controlled by the data analyst. Okay. Sometimes you fix this one. That's what it means, that, before I set off from the house, I have already fixed this, that I'm going to talk to level 100 people and level 200. Level 100 is what? Secondary school is 12. So level 100 is 13. Level 200, level 300, level 400. So you pre-populate here. So that's the meaning of X is controlled by the data analyst. So I can fix this already. Okay. Remember, it makes sense with the fertilizer, right? Before the farmer goes to the farm, he say, well, I'm going to put 13 kilogram on one of the plots, 14 kilogram on another one, 15 kilogram on another one, 16 kilogram. When I get to the farm, this is what I'm going to do. Then after 3 months, I will record the harvest. So that is a different way of collecting data. The guy has fixed the X column and is waiting to record the Y's. It's an easy way to solve the model than going with the random, where I don't know the kilogram I'll be using. I just have a table. When I get to the farm, I sprinkle the fertilizer. I say, okay, over here, there were 2 kilograms that were sprinkled here. Okay, I don't know this ahead. That's the difference. And what is cited here, the X is controlled by the data analyst, is what I've explained here, where the guy fixes X before he goes to the farm. Okay. Now, when you do that, only the Y becomes a surprise. Think about it. The guy has fixed the fertilizer already. I'm going to put 13 kilograms here, 14 here. And after 3 months, when the maize is ready to harvest, I say, okay, the 13 kg plot gave me these bags of maize. This gave me 5 bags, 6 bags, 7 bags. So this is the only surprising element. Okay, so the surprise comes from here and not here, because it's already fixed. Okay, in other words, that's the meaning of the last bullet point. There is a probability distribution for Y at each possible value of X. In other words, you can have 13 and 13 on 2 plots, 13, 13, but the harvest will be different. So there is a probability distribution for Y at each possible value of X. I cannot tell for sure what 15 kg will yield, but I know that there is going to be some harvest, which depends on the fertilizer. But I cannot tell for sure, of course, because of the error term U. Okay. We've done almost an hour and I'm still at slide 7. I was hoping I can get to slide 50. Okay. I'm hoping I'm laying a strong foundation and then we begin to jump. Let's keep going. Any questions so far? Okay. Are we doing pretty okay? All right. Now, so from our model, we call this the slope parameter. I told you from calculus, dy dx yielded beta 1, and therefore it is our slope parameter. Okay. Now, before you graduate from this course, you must know how to interpret beta 1. By how much does the dependent variable change if the independent variable increased by 1 unit? That is the meaning of beta 1. So if I specify this model, wage is not different from beta 0 plus beta 1 education plus the error term. if your level of education should increase by 1 year, then your wage will change by beta 1. That is how you interpret beta 1. That is the interpretation of beta 1. If education increases by 1 unit, unit here means the years. So if you increase your level of education by 1 year, your wage will increase by beta 1. That is how we interpret beta 1. Okay, think about it. When you do the derivative of wage, the education, the partial derivative, you have beta 1 plus du, the education. Okay, I'm taking partial derivative of this guy. Okay, you may have done calculus 3. If you did mathematics at Legon, we do this thing in calculus 3. So look at the partial derivative here. The wage, the education. Okay, you be left with beta 1. I'm differentiating with respect to education. And this is du, the education. So look at, of course, I've told you that what's the meaning of slope? How does y change if x changes? So that's the impact. If you go to school 1 more year, your wage will change by beta 1. Only if this guy is 0, right? Only if this guy is 0, this guy. Because when your education changes, you is also changing. So we say, there's a phrase we use. How did they call it? Holding all other things constant. That is the meaning. Okay, so when your level of education changes by 1 unit, your wage will change by beta 1, sorry. But only if the U also didn't change. Okay, so the simple way we say is that over here, let me go back to the generic equation. Here, if you come to our department statistics, you ask our graduate students that, oh, how do you interpret beta 1? They will say that if x changes by 1 unit, or let's say if x increases by 1 unit, y will change by beta 1. That's what they will tell you. And they will say holding other things constant. Okay. That's a full interpretation of beta 1. X increases by 1 unit, y will change by beta 1, holding other things constant. Now, when x is 0, then y is just beta 0. Okay, so that's the interpretation of the intercept. If x is 0, if you don't apply fertilizer, x is 0, your harvest is beta 0 for sure. You are guaranteed this average harvest if you don't use fertilizer at all. But beta 1 is the advantage or the impact of using fertilizer. Okay, additionally for those who use fertilizer, or what is the impact of using fertilizer? Okay, so please, you cannot complete this course without knowing how to interpret beta 1. It says when x increases by 1 unit, y changes by beta 1, holding other things constant. I did not say y increases because this beta could be negative or positive. So I just said changes. If x increases by 1 unit, y changes by beta 1. Okay, that's it. Okay, so that's pretty much for our foundation. Okay, this thing here, it is there because that is why we say all other things constant. When x changes by 1 unit, y changes by beta 1, holding other things constant. In other words, the change in u is also 0. Otherwise, beta 1 cannot be the only impact. The impact is going to be beta 1 plus change in u over change in x. This is the impact if x changes by 1 unit. Okay, it becomes only beta 1 if this change is 0. And that is why we say holding other things constant. If u is constant, the change there is 0. Okay. Okay, cynically or unfortunately, there's a statement here. The simple linear regression model is rarely applicable in practice. Okay, but its discussion is useful for pedagogical reasons. You know what a simple regression is? It's a regression model with only one regressor, and therefore it is hardly useful. How can you fit, let me see my next slide. Yes, look at this. How can you explain differences in yield using differences in fertilizer application, fertilizer are here. When you having control for rainfall or land quality or presence of parasites, yeah. How can you do that? Rainfall affects harvest or yield. Land quality affect the yield. Presence of parasite affect the yield. They are all in the error term because this researcher insists on using simple regression. If he wasn't insistent on using simple regression, he would have gone further to add beta to rainfall, which rather makes sense, plus beta 3 land quality. But if a stubborn guy or someone who doesn't know regression at all wants to study the impact of fertilizer on yield, and he insists on using a simple regression, in other words, only one regressor, then by default, he is assuming that all other things that affect yield are subsumed in the error term. And that is not acceptable. That is why we say here that simple regression is rarely applicable. It's not useful. You will rather use what we call a multiple regression that allows you to add more than one regressor. Okay. Over here, if the guy, maybe an undergraduate student doing his project work, studies the impact of wage on education, and he's using a simple regression, it means he has only one regressor. Okay. Then when he comes to my office, I'll say, do you know that intelligence affects people's wages? And you are using simple regression. So you've lumped all this, the labor force experience, tenure, work ethic, you've lumped all of them in the error term, and it's going to cause a problem. And I will show you why soon. So simple regression is not acceptable. It's useful under certain conditions, like the experimental design that my colleague taught you. That way you created an experiment, so you will not have much of a problem. Okay. Otherwise, this is not useful. Simple regression is not. We use it to teach, to lay a foundation. Okay. Now, a few things. Regression equations are valid only over the region of the regressor variables contained. So if you have fertilizer, 1 kg, 2 kg, 3 kg, you cannot be making comments about 10 kg because your data ends at 3. You cannot be predicting or making comments about 10 kg. You cannot infer that, oh, if you use 1 kg, you harvest 5 bags. If you use 2 kg, you harvest 6 bags. Then somebody asks you, what if I apply 10 kg? You say, I have no information on that because my sample ended at 3. 10 is too far from 1 to 3. In other words, regression equations are valid only over the region of the regressor variables. Most importantly, my dear friends, here, this is a crucial one. A regression model does not imply cause and effect relationship between the variables. Even
Yes,
though
boss. Good afternoon.
who is that? Is there a
Yes,
question?
Wow.
Dorcas, you are good. Okay. A regression model does not imply a cause and effect relationship between variables, even though a strong empirical relation exists. Empirical simply here means something you obtain from data. Okay, you can think of it as the opposite of theoretical. Okay, if I say theoretical implication of something, and I say, so you know what theory means already, you are a scientist. Empirical means I have used data. Okay, I have some evidence from data. So that's the meaning of empirical. We are saying
Hello,
that,
sir.
yes.
Yeah, please, can you explain the point 1 again? I don't think I really understood what you meant.
Okay.
Regression
So
equations are valid only over, yeah.
Yeah, we are just saying do not extrapolate. Do not make comments or inference over the range of variables that you do not have. Okay. So over here, if I want to study this, those do agriculture economics, they will collect data on the harvest, the yield from several farmers and the amount of fertilizer they applied. Okay, so if you look in Microsoft Excel, this is how the data will look. The graduate student will have yield in Excel. You have 5 bags harvested, 6 bags harvested, 7 bags, 8 bags. The one who harvested 5, you say, oh, how much fertilizer did you use? He said, I used 1 kg. These guys, I used 2 kg, 3 kg, 4 kg. So my point is, if this is the only data you have, and somebody says, if I use 10 kg, can you predict my harvest? We are saying that is usually not acceptable, because you see, you have 1, 2, 3, 4. None of your data point is close to 10. So you actually don't have the power the statistical power to make inference about 10 kg, 11 kg, 15 kg. Assuming, but you can actually talk about 5 kg, because you have 1, 2, 3, 4. These are pretty close to the number 5 or the number 6. So I can make predictions. That's what I mean. Okay. So if your data ends here, don't be talking about the impact of 10 kg. Okay. Don't be talking about the impact of applying 10 kilograms of 20 kilograms of fertilizer when your data doesn't have 19, 18, 17. You have nothing in the teens. You cannot inference about 20s. That's the whole point. Is this all right?
Thank you. Yes, please.
Sounds good. This is the important to me. Whenever you run a regression, the guy has run, I have a graduate student, MPhil, he graduated like 3 weeks ago, 4 weeks or so. He was claiming causality. You know, when there's a drought in northern Ghana, the harvest will come down. I said, no, you cannot talk about causality. Regression does not allow you to just talk about causality. That's the key point here, right here. Regression model does not imply a cause and effect between the variables, even though you may have seen a strong relationship empirically using your data. So regression is a statistical technique used to study association or relationship between or amongst variables. It doesn't say that one causes the other. For example, over here, I can say fertilizer predicts changes in harvest. Okay, I cannot say fertilizer causes the harvest to change. Okay, I can say fertilizer predicts changes or increased use of fertilizer is associated with this increase in harvest. We are saying that this regression is just a statistical tool. It can help you in the process of thinking about causality, but on its own, it cannot tell you about causality on its own. I think I captured that here. To establish causality, relationship between the regressors and the response variable must have a basis outside the sample data. For example, the relation may be suggested by theoretical considerations. Finally here, regression analysis can help in confirming a cause and effect relationship, but it cannot be the sole basis of such a claim. Let me attempt another explanation and move on. Look at this equation 1 and equation 2. The yield. The yield, I'm fitting a simple regression model. So yield is not different from beta 0, beta 1 fertilizer, plus an error term U1. Equation 2, fertilizer is not different from alpha 0. I'm changing the parameters because I'm doing a different specification. So instead of beta, I'm using alpha 0 and alpha 1. What to here? Yield plus U2. Now, when you run these two models in any software, you may have significant relationship, but one of them doesn't make sense. Equation 2 doesn't make sense. Differences in yield does not influence differences in fertilizer applied. It is the one that makes sense. Differences in fertilizer application explains differences in yield. Now we are saying that my grandmother, who doesn't know anything in statistics, should be able to know that equation 1 is the one that makes sense. Therefore, if I have a significant relationship here, then I can be thinking that, okay, maybe fertilizer causes yield. Okay, fertilizer causes yield. But that is because there is a basis outside statistics. In other words, you see here, you run the model equation 2, and the guy says yield causes fertilizer, right? That doesn't make sense. So that's the danger with just relying on statistics to claim causality. There must be a basis outside the statistics or outside the model, usually theoretically. Maybe Einstein has come up with a theory. So you have a theory and you are testing. That one, everybody knows what your Y is and what your X is. Here we've swapped the X and the Y. It actually has no theoretical basis. It is not supported by even anecdotal evidence. And therefore, if your student brought this to you as a project work and says this causes that, just because the statistics say so, it is wrong. Okay, that is what we actually mean by, sorry about that. That's what we actually mean by regression can aid in confirming a cause and effect, but it cannot be the sole basis. For you, okay, to establish causality, the relationship between the regressors and the response must have a basis outside the sample data. We all know education changes your salary, either anecdotal evidence or theoretically. So when you specify such a relationship and you get everything right, you may begin to talk about causality. But you cannot be asleep. Somebody wakes you up, shows you fine statistics, and says this causes. The surname.
Yes, Doc.
Okay.
Yes.
Okay, it's good to have you.
All right. Good to
Okay,
have you.
thank you. Wilhelmina is asking, please, do you mean use multiple regression if your independent variable are 2? Yes. Whenever your independent variables are 2, you have left simple regression. You are now in the realm of multiple regression. Okay. So please, anywhere in an exam, they ask you, there is a regression has been run, and they are asking you that fertilizer cause yield. You say no. We can tell that fertilizer can predict changes in the yield, but we haven't established causality yet. It may be that it is the soil fertility, the land quality, that is changing the yield, but supported by fertilizer. You don't know what causes what. If free SHS improves somebody's mathematics score, it may be because it's in the boarding school. It may not be the free SHS. So don't jump into conclusion yet until everything is satisfied. Okay, so the bar of causality is really high. You have to convince us. You have to convince us. One of my students, they went to secondary school for 4 years. Some of you here may have gone to secondary school for 4 years under President Kufuor or so, or President Mills. Some of you may have gone to secondary school for 4 years. Okay, if you are here, give us a hi, wave, you know. Okay, so somebody, I met one guy in the US, he's a professor. He said, well, those who went to secondary school 4 years, they did better, blah, blah, blah. Then I said, well, as an economist or somebody who does inference or reduced causal inference, I have a question for you. Did they do well because they are older? Okay, so did they do well? Did they do well because of the age effect? Maybe because they are now older. That is why they did well. So can you isolate the effect of the policy? President Kufuor brought a policy and maybe they did better. Fair enough. But as a statistician, it's not enough to tell me they did better. You have to tell me that this is not because they are now older by 1 year. It may be because of age effect. So you have to isolate the impact. Okay, look, I've isolated the effect. This is the impact due to age. This is the impact due to the 4-year policy. They completed the syllabi, blah, blah, blah. Then I'm happy with you. But if you do not disaggregate, and by the way, it is harder, right? You cannot isolate the effect of age from the policy. And therefore, there is a confounding factor, and you cannot claim causality. No serious economist will buy your story. Okay. So when students come to me, I tell them it's not possible to isolate the effect of the 4-year program. You cannot even tell whether the WIAC exams was the same for those who did 3 years versus those who did 4 years, and so on. So that's the idea of causality. Okay. Is that all right? Watson, DA. That's a nice name. Where's my slide? Okay. So where are we? Okay. So, my dear friends, you have fitted a regression line right here. Well, you took regression analysis with me, and therefore, for your thesis, you'll be able to specify this that yield related to fertilizer this way. But your aim is to know what beta 1 is. Is this 5? So that when a fertilizer use increase by 1 kg, you harvest 5 more bags. This is what you are interested in, beta 1. What is the impact? So this is what you are interested in. You want to have a value for it. Estimate this. Is it 5.1? Is it 6.2? I don't know. But I want to estimate it. So that's where we are approaching now. You know how to specify the model. All of you here now, you are now experts. You can specify a model. You know what your dependent is, what your independent is. You control for all other factors you cannot have as your error term. We are now going to estimate beta 0 and beta 1 so that I can tell the government that, look, if student enjoys free SHS, his core mathematics score increases by 1 percentage point. So the government say he's interested in this number. How do I get it? That's where we are going, estimation. Okay. So you specify the model this way. Okay. And then, by the way, if you have done some statistics, E operator here means expectation. It's talking about average, okay? Just the average. Look at this. My good friend, Prosper. I cannot Prosper if he's a farmer or he's in school. If Prosper applies 5 kg of fertilizer, I don't know the yield he will get because there's a random component. I cannot predict with certainty. There's a random component. This is a random variable, mean 0, constant variance. Prosper and Francis can apply the same kilogram of fertilizer. Their harvest will be different. So I cannot tell what Prosper will harvest, even if Prosper tells me his kg of fertilizer. Because this is unpredictable. I don't know. But there's a way around it. I cannot tell Prosper harvest, even if I know his kilogram. I cannot tell Francis on, but people like Francis, people like Prosper, I can tell you what they will get on average. Take it again. I cannot tell individually what Prosper will make because there's an error component I don't know. I don't know the rainfall. I don't know the parasite, pesticide on his farm. There are random things I don't. So I cannot tell Francis alone. But on average, people like Francis, I can. So that's where we are going. So look at this. I take expectation of our model. I put in the E operator. Okay, I put the operator through. Take the operator through. Okay, the operator can go through additively. Okay, so this will be repeated here. This will be repeated here. It will be repeated here. Look at the right-hand side. This is a constant. The expected value of a constant is a constant. Expected value means on average. Okay. On average, a constant is just a constant, right? 2 plus 2. What is the average of these numbers? Divide by 3, right? There are 3 of them. So divide by 3. You still get 2. So the average of a constant is the same thing. So the expectation when you operate on this constant is the same. When you operate on this is the same. So here some of you may be confused, but when I operate on this is the same because I assume X is fixed. Remember, I said the farmer can fix the fertilizer before going to the farm. So there's no random here. There's no surprise here. The variability is only in you. So only you have the operator with it. All these are assumed to be constant when x is fixed. Now, if I assume this is 0, if I assume this is 0, then I'm left with this. This looks like a familiar equation from your secondary school equation of a straight line, y is equal to mx plus c, where m is the gradient. Look at our slope parameter, mx plus c. So look at this, average. I cannot predict Prosper's outcome, but E means average. On average, given X, given people like Prosper, if there are 20 people, 100 people, okay, given that all these people are using 5 kg of fertilizer, I will be able to tell. So all the predictions I'm making are on average. I cannot single-handedly or tell you what Prosper will make, but on average, given X, condition on X, given that the guy looks like Prosper, given that his level of education is 10 years, I can predict on average what his salary will be. There is no error here anymore. So now this becomes deterministic. It's an equation of a straight line. I can use it to make predictions. I can use it to make predictions. But remember, it is doable because I assume this. And I'll come to this. This goes away. Okay. Where am I? Right. Oh, this one. What do I want to show? I want to show what do I? Oh, okay. So a straight line, something like this. I now have equation of a straight line, something like y equals to mx plus c. I can begin to make predictions. Give me Prosper's, somebody like Prosper's fertilizer. I will tell you what he will make on average. That's it. People like Prosper, give me their fertilizer X. I predict their harvest. That's it. Okay, so the two allows me to talk about people like Prosper on average, but it's hard to tell one person's own. Okay, so this we will refine our interpretation of this here. When X changes by 1 unit, Y will increase on average. Now I'm introducing the keyword average by beta 1. Okay, because I'm only able to recover averages. Awesome. I hope you are doing all right. So I've told you we are going through estimation. I'm looking for that beta. The beta 1, it's of policy interest to the president. If people enjoy free SHS, how does it impact their core mathematics score? So the president has asked me as an impact evaluation expert to tell me what is beta 1, or if people were to go to school 1 more year, how does it impact their wage? Then I say, well, go around, collect data. So, okay, I collect data, a random sample, okay, on people. When I meet you on the street, I ask you, what's your level of education and what is your salary? This is for Prosper, Francis, then Bernice, all of you. When I meet you in town, I ask of your X and your Y. So I have data plenty, and I take it to Microsoft Excel. I have your level of education you told me on the street, and then your wage that you recorded. So I have this data in Microsoft Excel, something like this. I've recorded it. So that's a random sample. I'm using it to study the impact of education on wage. You cannot do it without data. And we'll do some practice next time we meet, next Friday. Okay, inshallah. Okay. So what do I have here? Value of the explanative variable of the ith observation. I could be Francis, Georgette, or whatsoever. And y is the dependent variable, okay? By now, you must know what is a dependent variable and explanative variable. And when you specify the model, you must know it. Where am I going with this? This is where I'm going. I want to tell the president the impact of fertilizer. Yeah. Is there a question? Is there a question?
You should press this one.
Helena is talking. Is there a question? Okay, there is one Abdul Malik. Is that my friend from Medina? Probably not. He's an accountant. I don't know. He's probably not going to be here. Okay. So this is where I'm going.
Sorry, right, Doc. Just before you go on, I was expecting that. I don't know whether that's where we're heading. on slide 11, when you showed that simple equation of a straight line, that if we know we can predict the yield from the impact of the yield from the fertilizer, but then how do we determine the beta 1?
That's where I'm going, sir.
Okay, right.
Good question. That's where we are going. I want to know beta 0 and beta 1. These are the parameters of interest. So I collect data on this slide 12. I've collected data. I saw, well, I've been to Afram Plains. I collected data from farmers on their yield, fertilizer, and so on. I can actually show you if you give me a minute and look for the farm. So you can collect data on farmers. They report their yield and their fertilizer. You have it in Microsoft Excel. Then, boom, we are looking for how to estimate beta 0 and beta 1. There are several techniques, but one of them does an excellent job. So I will show you that one here. We call it the ordinary least square. Ordinary least square. Think about it. I said this is the data, right? Farmer Francis, Farmer Prosper, Farmer Helena. So this is Prosper, right? So Prosper's fertilizer is here. Okay, you've done mathematics, so you know how to plot data point. If he tells me his fertilizer is 2 kg and his harvest is 5, then you locate on a graph sheet. You trace from 2 to 5, and then you mark the point. So that's how these points were obtained. So this for Francis, Prosper, and so on, Helena, and so on. Okay. Now, I want to estimate beta and beta 1. There are several ways. There's one particularly useful technique. We call it the OLS, the ordinary least square. So please pay attention. When you fit, okay, when you fit the line, this line through the point, just a line of best fit. So I've plotted the point, your data, all of you have plotted the point in a scattered diagram, and I want to fit this line. This line here, okay, is our headache. That is why we are here this afternoon, actually, to get this line. Remember, it is a equation of a straight line. Y is equal to mx plus c, something like that. If I know c and m, I am done. I can predict x. I can predict y, given x. So this is my beta 0 and beta 1. That's what I'm doing. Ordinary least square says, look, I want to be close to each of the points. Okay, I want the line here to be close to all the points, as close as possible. That is the technique, the ordinary least square technique. Okay, it says you want the line to be close to the point as much as possible. In that way, you'll be able to predict them quite accurately. Okay, take a straight line, for example, y is equal to 2x plus 3. What's an example of a point on this line? The point 0,3 lies on this line. When x is 0, y is 3. The point 0,3 lies on this line. If this line equals to 2x plus 3, then I'm saying this point 2,3 lies on the line. So if your line can actually go through all the points, then you can predict accurately. Because if you tell me x is 0, I'll tell you y is 3. That's like a perfect deterministic prediction. Okay, but unfortunately, your line cannot pass through all the points accurately. So you want it to pass. You want to pass it through. Okay, kind of like the middle of all the points. It should be close to all of them. Okay, as much as possible. In other words, assuming this is my line, this is Francis's y. This is Francis's y, the actual y, because it's from the data. But the line is what I will predict for Francis on the line. Okay, so it was y is equal to 2x plus 3. If Francis told me he used 5 kg of fertilizer, I predict this, which is 13. It might be that Francis applied 13 or not. Maybe he applied 15, but the line that I fit says 13. So we are here. Then we have a discrepancy, or what we call the error term. Y minus what I predicted for it. This is the y hat. Y minus what I made, the forecast I made. Y, the actual y of Francis, minus what I predicted for him is the residual. I beg your pardon. It is not the error. it is the residual. In Francis's case, it will be 15 minus 13, which is equal to 2. Now, this ordinary least square technique says, look, I want to be close, I want the line to be close to Francis's point as much as possible. In other words, I want to reduce this 2. This surplus 2, I want to bring it to 0, if possible. That is it. Because if this goes to 0, then I hit the target, right? If y is the same as y hat, then the difference, it will be 0. Then that means all the time my prediction is accurate. It may not, but I want to minimize this gap. This is actual Francis. This is my prediction for Francis. I want to minimize this gap. That is what the technique is doing. So fit the line through the point, okay? But I want to be close to all the points as much as possible, and that way I minimize the residuals. That is it. That is what the technique is doing, okay? Over here in the PhD level, I derive it here, PhD statistics. But here, I'm not going to derive that. I'm just giving you the flavor of what the technique is. Now, so you may remember from your elementary statistics right here. Look at these numbers, X. Somebody should find a mean for me. 1, 2, 3. What is the mean of these numbers? What is the mean? Quickly.
1.5.
What's the average of these 3 numbers, sir? Who has it? What's the mean of the, oh, sorry, this is 3. What's the mean of these numbers? 2, right?
2.
The mean is 2. Let's do x minus x bar. X minus x bar. X minus x bar. X minus x bar. So this becomes what? -1, 0, 1. When you sum them, what do you get?
You
get 2.
No, 0. When you sum this.
Okay, you get 0.
0. Yes. So whenever you take a number, deviations from mean and sum them, they tend to go to 0. It's a problem. It's a problem. Whenever you sum deviations from the mean. Remember I told you that our line of best fit is pretty much the average, right? So this is actually the mean. So deviations from the mean. This is Francis. How Francis deviates from the mean outcome. Maybe we had positive 2. Prosper's own might be -2. Then they sum to 0 all the time. Deviations from mean sum to 0. Okay, this is a statistic regularity. It's always summing to 0. Because of that, the ordinary least square goes a step further and says this. Okay, it says what? They are minimizing sum of the square residual. So I think who is that talking there? Who is that? I can always figure out. Okay, it's gone off right now. Okay. So we are minimizing sum of the square residuals, right? I want to be close to all the points as possible to minimize the distance from the actual and the prediction. So I'm minimizing the residual. So for all of them, I'm going to sum their residuals. I've told you, I've shown you when you sum residual, x minus x bar, which is the residual, they are always going to be 0. And for that matter, instead of just summing y minus y hat, which will be 0 anyway, we'll just square it. That's it. So that's what a technique does, ordinary least squares. It is summing the sum of the squared residuals. It is summing them because the sum will not vanish. When you don't sum it, I've shown you, okay, that deviations from the mean always vanish. Okay, in mathematics, when we say something has vanished, we mean it goes to 0. Okay, because of that, the technique squares the residual, okay, and then sums them. That is what the technique does. Okay, my dear friend who asked about the estimation. Okay, by the way, there's something technical here. When you see this, when you see this one, it means that I have collected data because I put I. So I is Francis, Janet, Benis, that's I. When I leave it like that, I'm not saying I have collected data yet. I'm still in the population. This is how fertilizer relates to yield in Ghana. Okay, in the data I've collected, let me see. Okay, I was going to go to slide number 50. I'm now at 15. It's crazy. Okay, but it's all good. Now, when you minimize some of the squared residuals, this is it. This is U hat. So what is U hat? Residual. Actual minus predicted. Y minus Y hat. This is the residual. So we are squaring the residuals so that they don't vanish. And then we sum them. I am minimizing them. You know why already? Because I want the minimum, of course, I want to minimize this gap. I want to minimize it so that my prediction is always close to the actual. So that's why the minimum, the objective function is being minimized and not maximized. You cannot be maximizing your margin of error. That's crazy. When you minimize that, that is how you get your estimators, beta 0 hat and beta 1 hat. Unfortunately, I don't show you the derivation, okay? But that is how, actually, here in Department of Statistics, the students derive it once in their lifetimes. After that, they use the software to run them for the estimate. So I'm going to run some for you to see, probably not today, but that is how the estimators are derived. And by the way, this is how the estimators look like. This is how beta 1 looks like. Okay, this is how beta 1 looks like, and this is how beta 0 looks like. Okay, in other words, this is what our computer will be using to tell us our beta 1 hat and beta 0 hat. Okay, it says that, look, if you have data on your X and your Y, okay, it is telling the computer that create another column for X minus X bar. So it will tell the computer that please create X minus X bar like I did. When you are done, create Y minus Y bar. When you are done, create another column that multiplies them. These two, create another column that multiplies them on the right. When you finish multiplying, please sum them. When you sum them, keep it for me as my numerator. Then the X minus X bar here, create another column that squares them. When you are done, sum them. Please keep it as my denominator. And that is my beta 1 hat. So that's the formula. That's the ordinary least square estimator of the slope parameter. Okay. Once you get it, it says, well, what is the average harvest in the data you've calculated? Give me Y bar. Anyone who has done commerce in Ghana know how to find Y bar and how to find X bar, given a data. And I have beta 1 hat already, so I can have beta 0 hat. That's how the parameters are estimated. Okay. Any questions? A bit of speeding, but it's fine. I think once you get a flavor, you'll be fine.
Hello, Doc.
Questions? Yes, go ahead, sir.
Please, is there any
Alex,
difference when we see the hat and the bar?
Yeah, the bar is the average, right? If you collect data, if I ask of your GPA and I calculate the average, it's just the X bar. That's your GPA bar or Y bar. That's the average. That's the average of your GPA. So that's elementary X bar. That's it. Okay, I don't mean elementary in condescending manner, but I mean X bar, as we know in statistics, is just the average GPA, for example. So you add Y1 plus Y2 all the way up to YN and divide by the sample data point. That's always the bar. The Y hat is the prediction, okay? Is a prediction. So now I have beta 0 hat. Oh, okay. By the way, let me finish with this. So if you want to study the average GPA amongst you people without the help of any variable, you can go with the Y bar. But if you want to study GPA based on people's secondary school they attended, then the regression comes in because you are adding regressors like the secondary school they went to, the agenda, and so on. Okay. So Y hat is different from Y bar in the sense that Y hat is now a prediction because I'm using an X and I have my parameter estimate and I predict, okay, like somebody's salary or predict the fertilizer use. Okay, Y bar will be the average in the data. And remember, what they say, or what is the average? What will be the weather? What will be the weather tomorrow? Well, I don't know. I'll use the average for August, the month of August. I can use that. Or I can waste time and do regression to predict the temperature for tomorrow. That's what I'm saying. Something like that. Okay. I hope that helps.
Yes, Doc.
Okay. So who is that, man? We are having fun here. Okay. Or you are not having fun. Okay. Let's keep going. Now, this is a technical point that the one with the heart, the solid line, it is the one you know. When you run the OLS estimation in a computer, it is the solid line that you have estimated. Okay. You have no way. This one, this is called a true, the unknown population. How? Oh, did I skip? I skipped a page, but let me talk about this. How? Forget about it. Okay, this is return on equity. Okay, investment, return on equity and salary. If you are a boss of a finance firm, if the return on equity is doing well, we want to see how that increases, how that impacts your salary. If this is doing well, your owners may increase your salary. So what's the impact of return on equity on the manager's salary? We are saying that when we run the regression, when you have the heart, okay, this is what you have recovered. Okay, the fitted regression line. You can never know the dotted one because that is unknown population. How education is related to salary in Ghana, you can never know for sure. It is unknown, but you can try with a regression line. Of course, if you know it, then you just predict. So the point here is that, look, you may actually be off. Look, this is off. The solid line is what we predicted, but this is the true. The true looks like this, and we predicted this. We are actually off, okay, by some units. So that is the whole point, that the farmers example, farmers from Afram Plains may give you this line, and the guy will go and use farmers from Tamale, it may give you this line. So there are things you must do so that you have a line. You hope, okay, that Salome, you are writing on the screen, okay, we don't want that. So what is the point is that our beta 0 and beta 1, they have desirable properties that on average, we hope that they are close to the true, they will give us the true population line, okay? But we are saying on this slide that remember that just a single set of data from our Afram Plains or Tamale could be off, okay? And you actually never know the true line to compare with, okay? So just be careful. But there are massaging things you do that on average, I hope I am close to the true line, okay? But if you are taking an exam, multiple choice exam anywhere in your lifetime, the true population line is never known. It's a fatal line that we know. We don't even know how good we are doing. But we hope that if you are using the sum of square residuals OLS technique and all desirable properties are met, then you are close to the line. Okay. So let me go back here. So we have a bit of a practice here. Okay, here, this equation here, regression model, has been estimated. We call it a fitted. So this is the population model, population equation, and this is the fitted model. We have now fitted it to data. Okay, so I want you to know the interpretation of this. The CEO salary is in thousands of Ghana cedis. So look at the interpretation. If the return on equity, this variable, increases by 1 percentage point, then salary is predicted to change by 18,501. Okay, we have multiplied this by 1,000 because this data is in thousands. Okay, sometimes you don't want your data in Excel to have 1 million, blah, 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 blah. These are long numbers. You can divide all of them by 1 million. When you get a number like this, you multiply by the 1 million. Okay, so here they work with numbers that were deflated, but at the end you must multiply by the 1,000 because the salary is in thousands. So please know how to interpret this. Okay, this example is a bit not good because it has introduced some dynamics. Let me go for this one. Okay, please look at this. You must know how to interpret this one. The model is fitted for you. What does it mean? In the sample, 1 more year of education is associated with an increase in hourly wage by 54 pesos. Okay, so if the model is estimated for me, then they invite me to the Jubilee House. My advisor when I was in graduate school in the US will be invited to the Congress, the US Congress, to talk about importation, how the US is faring. Okay, sometimes I did the analysis for him. So when you get there, you say, well, sir, these are my results. If somebody goes to school 1 more year, on average, his hourly wage will increase by 54 cents. You say, oh, okay, interesting. And then they will raise a protest. You didn't tell us about his work experience. You didn't tell us about tenure. You didn't tell us if the guy is a smart guy. You didn't tell us about his gender, when we know there's gender discrimination. Okay, so that then they will throw away your simple regression as being useless. They will say, go and use multiple regression. Okay, but my dear friends, you must know how to interpret equations like this, okay, at the barest minimum. Okay, so I'm back here. Okay, look at this one again. This one says, by the way, I have 72 slides to finish this module. We are at 18, but we will see. Now, look at this. If education increases by 1 unit, here the unit is known, years. Education is measured in years. So an additional year of education predicts our increase in hourly wage. Here, is there a question? Oh, and here also, let me go back. Somebody with no education, when your education is 0, then you are making 90 cents per hour. Okay, but the guy with 2 people, one with a higher education than the other, makes 54 cents more. Okay, so with no education, you are making 90 cents. When government announces minimum wage, it's usually for these people. It's binding on them, or teenagers who finish secondary school and are doing mobile money. They get a minimum wage. Okay, but an additional year of education predicts an increase in your wage by 54 cents. Here, okay, look at this. The interpretation is a bit weird. Do you know the difference between percentage point and salary? Okay, this is if your salary moves from 100 cedis to 120, your salary has increased by 20%. Okay, but if they say unemployment rate in Ghana is 15%, it's now 20%, then it has increased by 15 percentage points. 15 percentage points. I don't know the percentage increase yet, unless I do it. What would that be? 20 minus 15 over 15, right? Times 100%. When I do this, I can tell the percentage change. But when you eyeball it, you can only use the language of percentage points. This has increased by 5 percentage points, not 5%. You have to do this mathematics to know the percentage change. So it's a technical language. I hear people on TV, I just laugh. Some of those politicians, it makes them and so on. Okay. Because this data was recorded in percentages, that is why he's saying, oh, a unit change. Over here, the unit is in percentage points. For example, if this were inflation, inflation is already, when you look at Microsoft Excel, inflation is already reported in percentages. So I can only talk about percentage point change. Okay, so hopefully that makes sense. Let's keep going. Let's keep going. Okay, very exciting to me. I don't know about you, but okay, so this is very important. My boss will be angry if I don't go over the assumptions. So I've talked about beautiful things about a simple regression. All of you here, let me see what my level 400 students are doing. Okay, so one of them, Mary, cool stuff. She's studying that, during the COVID, people didn't go to hospital for other issues, like the eye crown. How did they call the eye? The dentist is the teeth, right? Optometry or whatever. The eye doctor, teeth, the dentist, and so on. So my student is hypothesizing that, look, because of the COVID, people didn't go for some care. They stayed at home. They were scared. So what's the impact of COVID on hospital attendance. So she specifies a model. She comes to me and she specifies the model. She goes to the whiteboard and specifies the model. She has hospital attendance on the left-hand side. Hospital attendance is equal to beta 0 plus beta 1 COVID-19. Very interesting. Cool. She got very cool stuff. So I don't have the workout. I've shared with you. Then blah, 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 error term. She's checking out how the presence of COVID impacted attendance to hospitals or admissions to hospital. Okay. What am I driving at? At this stage of our lecture, you should all be able to write down your simple model. Write down your model like this. Whatever you are thinking about studying. You know how to estimate this because you use the ordinary least square, which the computers will do for you. At this point, you know how to interpret beta 1. My students found that during the COVID era, okay, this beta hat, they got a negative number. Okay, in other words, the presence of COVID is negatively related to hospital attendance. Whenever there was COVID, people went to hospital less. That's what she found. She has interpreted the result beautifully. Okay, now for us to trust the results, there are assumptions we make. First of all, the model must be linear in the parameters. I've explained this. Here, beta 0 and beta 1 should not be squared or square root or whatever. The model you are running should be linear in the parameters. By the way, even if she adds plus beta 2 x squared, although this makes it a quadratic model, we still call it a linear regression. Why? Because it is still linear in the parameters. So the word linear regression is not contingent on the regressors. The linear in parameters means linear in beta 0, beta 1, and beta 1. This is, of course, a quadratic model. It is also another form of non-linearity, but it doesn't take away the fact that this is a linear model. Why? Because it is linear in the parameters. Very important. So your model must be linear in parameters for you to have the desirable properties of the estimate you are making. And so that you can trust your results, you must satisfy some assumptions. 1, the model must be linear in the parameters. 2, there must be sample variation in the explanatory variables. Of course, how can you seek to explain differences in yield using differences in fertilizer? I want to explain differences in the yield using differences in fertilizer. So you should not have this being the same number. It should not be the same. Otherwise, it doesn't make sense to say you are explaining differences in yield using differences in fertilizer. Your fertilizer numbers have no differences. They are all the same. So it is a second assumption that there is sample variation in your explanatory variable. This number should not be 0. In other words, this number should not be constant. If they were, this thing will go to 0. Okay, so we are saying the deviation from the sample mean should be positive. At least you cannot do a regression with constant regressors. Okay, a very important one. Some of you are following me. You will notice that I assume this thing to be 0 when I was recovering the regression line. So it's an important equation, assumption. Okay, it has some deeper meaning, but students tend to understand the watered down version, which says the error term should not be related to your regressor. The error term should not be related to the regressor. The error term should not be related to the regressor. Okay, if they are, there is a problem. Okay, if they are related, right? If they are related, think about our model. What will be dy dx? Dy dx will be beta 1 plus du dx. Because this is, if this is not 0, then this exists. There is a du dx. Therefore, beta 1 is not your impact. It's beta 1 plus something, a noise. You don't know you, so it becomes a problem. That is why we always want this guy to go to 0. This one, we assume this is 0. Okay. Then when I get my beta 1, I know this doesn't exist. I can confidently say beta 1 is the impact of the regressor. Okay. I'm getting tired. We'll be out of the door in 10 minutes. Okay. Now, there's a good news. Under the assumptions I've shown you so far, linear in parameters, variation in your regressors, and the third one is a 0 conditional mean assumption here. The regressor should not be related to the error term. Under those assumptions, we say the estimators we get, beta 0 and beta 1 are unbiased. Did any of my colleagues talk about this unbiasedness and variance of estimators? Hello, Francis.
I'm not too sure that it was mentioned anyway. Sorry.
So this is a desirable property of an estimator. Remember, I want to estimate beta 1. Beta 1 is the impact of fertilizer on yield. I am hoping that the estimator I am using is the OLS estimator right here. Right here. This is how I am estimating beta 1. I want my estimator to be unbiased. In other words, on average, the estimator should give me values equal to the true parameter. Look at this. On average, that expectation of this estimator should be equal to the true parameter. The true has no hat on top of it. The estimates have a hat. Okay. So that's the difference. The true parameter have no hat or cap. This has a hat. So on average, I want beta hat to be equal to the true parameter. On average, I want beta 1 hat to be equal to the true parameter, population parameter. And we are saying that the assumptions we've seen so far, 1, 2, 3, 1, 2, and 3. If these are satisfied, you are guaranteed that your estimators on average will be equal to the true parameter. So that is exciting, a good news. If I collect data on farmers, okay, let's say the true parameter, take this for example, the true GPA, the true average GPA on Legon campus. All the students is known by the registrar, but he will never tell me. Maybe it's 3.8. He will never tell me. I will go to BAM library, collect data on some students, take the average. I may get 3.4. I can also go to the law school, collect data on students, calculate their average GPA. I'll get 3.9. So a single sample may deviate from the true. A single sample might deviate from the true. But on average, if I were to do this, this is where, I said this is where, BAM library, this is the law school. Look at our Bush Canteen. Look at Commonwealth Hall. They are smart people. Look at Equaf. Let me give them 3.4. I'm just kidding. I'm a fellow of Legon Hall. So Legon Hall is what? 4.0. I'm saying that all these numbers, 1, 2, 3, 4. If I do this repeatedly, Commonwealth, voter, blah, 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 blah. On average, I'm hoping like this. I'm hoping, okay, the average of all those voters come off will be equal to the true parameter. But I am conceding that a single estimate from voter hall will deviate, may deviate from the true. Fair enough. Okay, but this unbiasedness actually means that on average, you are hitting the target. Okay. I hope it helps a little bit. These are high-level statistics, so it's okay if you just have a flavor. Okay, no, don't need to worry yourself. There is a fourth assumption called homoscedasticity. Okay, so I'm going to end with the assumption. This is homo, and so I'm gonna end on slide 25. I was targeting 50, but we'll see. Okay, yeah, I'm gonna end at 25 right here. This is a good place to start next time. So homoscedasticity, what does it say? The variance of the error term is constant. Look at this. The variance, this is variance. Variance of the error term does not depend on the level of the regressor. If I had put xi here, or something involving I here, it means variance of the error term depends on I. Remember, I means Francis, I means whoever. But we are assuming that variance of the error term is constant. It also has an implication. It gives us the desirable properties we need. So I'm going to throw more light on that. Okay, it's the next technical thing, and the rest is straightforward. Look at this. What is this? Food expenditure income. This is income and food expenditure. So I'm going to show you a graph of a scatter plot of how much people spend on food given their income. First of all, look at this pattern. This has no any pattern, okay? It has like a mean of 0. Looks like this point have been spread here randomly. So this is the homoscedasticity. This is what we want, the variance of the error term. Or when you plot the x and the y, the data should look like this. Then you have homoscedasticity. Homoscedasticity. Homo means what? One, or sameness, homogeneity. So this is homoscedasticity. This is what we mean by the variance of the error term being constant. When you plot the data, you should see this. This is not the error, but when you plot the data, you should see this. And this is indicative of homoscedasticity. I want to show you next the violation of homoscedasticity, also called heteroscedasticity. Heteroscedasticity. Now, you realize that so what I just cleaned, you see that there is no pattern between the level of income. This is 0 cedis and this is 100,000 cedis, right? There is no pattern. You don't see any pattern that, oh, as income is increasing, people are spending more on food. There's actually no pattern. Look at somebody here at 100,000, he's spending less. Look at somebody here at 10,000, 100 cedis, he's spending more. Okay, so there's actually no discernible pattern. Now, so this is homoscedasticity. This is what we want. I want to show you heteroscedasticity, and then we close. What is hetero? Hetero says, well, homoscedasticity has been violated. In other words, there is now a discernible pattern between your regressor and your explanatory variable. So you can see this is opening like a funnel or funnel, as our old women used to say. So this is opening like a funnel shape or like a bell. It is opening wide. At lower levels, you see the numbers are also small. The variability, there is variability is small. Then, boom. What is the point that, look, all those who make 800 Ghana cedis income, the amount they spend on food is hovering around the same. The guy is making 800, he probably spends 400 cedis on food. All those in the neighborhood of 800 to 1,000 Ghana, there is no much variability in how much they spend on food. You see, they are closely packed. Yeah, there's no much variability. Somebody is making 800 Ghana, he spends 400. Somebody is making 900 Ghana, he spends 450. There's no much variation. And it is true, people who make small money, there's no variation in their food expenditures. But when you get to higher income, then you see higher variation. Of those making 100,000 cedis, some may spend only 10,000 on food. Some may spend as high as 50,000. So I'm saying that there is space. There's a wider space. Wider space. Look at the gap. When you get to higher income level, for those people, things change. But these people, there's little variation. This is heteroscedasticity, a violation of homoscedasticity. Okay. So it is clear now. It should be clear by now, my dear friends, what homoscedasticity is. You see, so the variance of the error term given x is constant. Okay, and hetero means it's violated. Okay, now under the assumptions I've shown you so far, from 1 to 4, Okay, I haven't seen your faces because it's on Zoom, but when I meet you in town and I ask you what are the 4 assumptions governing the simple linear regression, you can list some of them. If I meet you, I had a student at Fidelity Bank. When I got there, I asked him to list some of the simple linear regression assumptions just for fun. He was able to remember. It says 1, linear parameters, 2, sample variation, 3, 0 conditional mean, and 4, homoscedasticity. If all these assumptions are satisfied, okay, if all these assumptions are satisfied, then we say we have a blue, okay, estimators. You see our estimators of beta 0, the OLS estimators of beta 0 and beta 1, we say they are the best linear unbiased estimators. So if these assumptions hold, then you have the best. There's no way to improve on your estimators. If your estimator says returns to schooling is 94 cents, 54 cents, if you go to school 1 more year, you make 54 cents, then we believe that because these assumptions are satisfied. And when the assumptions are satisfied, you have the best linear unbiased estimators. So we just believe your estimate and we take it like that. It is only when 1 or 2 of the assumptions are violated that I would doubt your estimates. But if they are satisfied, there is a theorem called Gauss-Markov. This should not be there. Gauss-Markov theorem. It says our OLS estimators are best, are blue, blue. Blue is an acronym. Blue for best linear unbiased estimators. Why are they best? Because they have the smallest variance. Why are they linear? Because they show up as linear in the data. Look, this thing here is linear in Y. You don't see X squared or Y squared. So it's linear. That's where, look at this. It's also linear in the data. This is Y bar and X bar. You don't see square or whatever. So they are linear. So they are best because they yield the smallest variance. If there's time, I'll tell you about smallest variance. They are linear because the estimators are linear in the data. They are unbiased. I've shown you on average, they are unbiased, okay? Estimated. Best linear unbiased estimators. Our estimators are blue, okay? So my dear friends, I'll use the next 2 minutes to talk about this and then we'll draw the curtains, okay? So this is the variance of the estimators, okay? This is something technical, but think about it. You've done basic statistics. You know what a variance of a data is. Yes, we have an estimator. It also has its variance. Okay. The true GPA at the registrar's office will be 8.9. Commonwealth gave me 3.4. Volta or 3.5. Lego or 3.6. So I have a lot of data. How do all this differ from the average? So the estimator also has its variance. Okay, how it varies and so on. Okay, the same estimator is giving 3.4 from Volta, 3.5 come off and so on. So there's variability there. So we study variance of estimator. They look like this, okay? No need to remember. And therefore, once there's variance, there is standard deviation. Technically, when you have data on the whole population, you can use the language standard deviation. Once you have a sample, you have to use the language standard error. Okay. There was one statistician on TV when during the elections, they asked him his model. He was talking about standard deviation. One of my colleagues drew my attention that, look, this data is from election. It's not the whole Ghana. Why is he saying standard deviation? He has to use the language of standard error because it's coming from data. So standard error here of an estimator is, remember, standard deviation is always the square root of the variance. Okay. So something like this. It will be useful next time we meet for inferencing. Okay. Otherwise, if there is no question, I'll stop here. Any questions, Francis? Any questions? Abdul Malik, Abraham, Amenin, Jubala, Gordon, Anthony, Bernadette, Bernice, Bismarck, Caroline, Celestine. Any questions? Feel free. Charlotte, Comfort, Daniel, Forjo, Diana. Any questions? Those in computer science, you are close to me, we can stop by, Okay, any questions? Franklin, Frederick, Hamdia, Are you my student from Ashaleboche? Probably not. I'll be excited. Kafui, any questions? Mame, Henry, any questions? Iram, Jennifer, Essie, any questions? Eric, Ilya, any questions, folks?
No question from my end.
Okay, who is Development Institute? Pelnyak, any questions?
This is Ken.
No question.
Okay. All right, folks, we'll stop here. If you want to have more fun about this, we'll meet next week.
Okay,
Doctor.
thank you.
Of course, if you have my number, let me know any feedback, maybe whatever. we improve
Thank you,
next week.
Doc.
All right.
Okay, thank you very much.
Bye-bye.
Thank you very much.
Recording stopped.
Thank you, Doc.
Bye, Doc.